in patho and all the classes that we have gone through, respiratory acidosis, first of all, which is the value in the ABG that represents respiratory? CO2, right? So therefore, for you to get, and CO2 is the value of acidity, right? So in order for you to get respiratory acidosis, you have to accumulate CO2. So you have to retain CO2. You know that we breathe oxygen and we exhale CO2. Therefore, the only way to retain CO2 is if you're not breathing appropriately, at an appropriate rate. That means that you're breathing very, very slow. So now knowing that the only way to retain CO2 is to have your respiratory status decreased and your mental status being affected, let's start with the physiological causes of retaining CO2. What about breathing slowly when you're sleeping, right? So in physiological sleep, patients do retain at least 2 points higher than 45 of CO2, but that's completely physiological. Again, knowing that the state of sleep, physiologically, the patient will retain CO2, just think about what are other pathophysiological times that the patient is sleeping too much, and that's the reason why there's more retention of CO2. I'm at this level, okay, at the elementary level. So, what about if you give opioids to the patient? Right? What about if you sedate the patient with hypnotic, right? So narcotics, sedative hypnotics. Huh? Yeah. Any sedative hypnotics, any opioids or narcotics are going to put the patient on state of lethargy, right? Or somnolency, and therefore there's retention of CO2. What about the actual brain being affected, medulla and pons that control the respiratory rate, because the patients would have a traumatic brain injury, or the patient would have a stroke of either kind, right? Either ischemic or hemorrhagic. What about patients that are alcoholic? When you're drunk, not only you are talking stupidity and you're dizzy, but you go to sleep faster, right? So, ETOH abuse, seizures, because not only that, at the state of seizure, the patients cannot control the airway, therefore, the exhalation of CO2 doesn't happen. And that's the reason why the patients can retain CO2. So those are the causes of respiratory acidosis. Instead of me reading it on the PowerPoint, let me make you think, okay? Now, going over respiratory alkalosis, think about the opposite. Think about states, pathologically or physiologically, that the patient will breathe too fast. And that's the reason why the CO2 is exhaled out too fast. First of all, anxiety, right? Any panic disorder, pain, fever, or any type of toxic drum from the excitatory part, right? Like amphetamines, cocaine abuse. So think about states of excitability that the patients can breathe fast, okay? In addition, remember that respiratory alkalosis is also a compensatory state of metabolic acidosis, right? Kussmaul respiration, that you memorized that. Going to metabolic disorders, you have metabolic acidosis, okay? And the metabolic acidosis has two types. You have high anion gap metabolic acidosis, and you have non-anion gap metabolic acidosis. And that's really important to know based on anion gap calculation. And an ion gap calculation, the only thing that will tell you is the etiology, which is a question for your test, okay? So the only reason why you're calculating an ion gap is you need to know the etiology of that metabolic acidosis. Because if I tell you now that high anion gap metabolic acidosis will be related to methanol abuse or ethanol abuse, that is related to uremia, which is renal failure, and that renal failure, most likely end-stage renal failure, chronic renal failure, that is related to, for example, salicylate toxicity, that is related to iron toxicity, or isoniazide toxicity, or that is related to diabetes ketoacidosis, that is related to lactic acidosis. I'm just talking, okay? We're gonna go through the PowerPoint in a second. Why is it important to know if it's coming from diabetes ketoacidosis or lactic acidosis from sepsis, or because the patient is having a disease process that the patient is building up more and more lactic acid because it's going through an anaerobic cascade, than if I do have metabolic acidosis because the patient is having diarrhea.
It's gonna mark how you're gonna treat it.
It's going to mark how you're going to approach this patient treatment-wise. Do you understand? Okay. So that's exactly how we're going to talk about calculation of an iron gap, and then after that, we will calculate delta gap, because in patients that have metabolic acidosis, believe it or not, you will see, and I will prove it to you, that you can have metabolic acidosis purely related to high anion gap, for example, patients with diabetes ketoacidosis. But what happens with the patient with diabetes ketoacidosis? You have learned that hyperglycemia, glucose being high in plasma, is an osmotic substance, right? That brings fluid to the interstitial space, and the patients will start urinating, and large amount of urine will come out, and the patients will be dehydrated due to that. Yes or no? What's the reason why you give so much fluid to the patient with diabetes ketoacidosis? Because the osmotic gradient is so high by having high glucose level that the patients will urinate so much, and the patients will get dehydrated. Well, let me tell you that dehydration is the leading number cause of metabolic alkalosis. So therefore, listen to me, you can have patients with metabolic acidosis and metabolic alkalosis at the same time. And the only way to prove that is by calculating delta gap. In addition to that, can you have a patient, because the patient is in end-stage renal failure with uremia, right? By retaining uric acid and retaining urea, and you have a patient with end-stage renal failure with uremia, and the uremia causing metabolic acidosis, but this patient is now vomiting. I received a patient like that this weekend. The only complaint the patient had was vomiting for the past 2 weeks. And the patient thought it was a gastroenteritis. It was diagnosed like that by the attending. Okay? And just told the patient hydration and the Maalox and all that. And the patient went home. The patient kept vomiting. Patient went to the urgent care, and they did labs, and the BUN was 159, and the creatinine was 6.7, and that's the reason why the patient was vomiting, because of the uremia. So if you have uremia, that's a cause of high anion metabolic acidosis, but the patient was vomiting for the past 2 weeks, dehydrated, cause of metabolic alkalosis, right? But what about if it's not vomiting and the uremia will give the patient diarrhea? Well, In that case, remember you have pH, alkaline in your GI tract. When you eliminate that alkaline pH, you become acid, right? So a patient with uremia can have a high anion gap metabolic acidosis and a non-anion gap metabolic acidosis at the same time due to the diarrhea. I understand that the only concern that you would have to treat the patient in this case would be dialysis emergency, right? And I know that. And I know that as soon as you correct the uremia, the diarrhea is going to be corrected, or the vomit is going to be corrected, because you can't give a lot of fluid on this patient, right? Do you understand? I want you to know by giving you those examples that the patients are not an isolated acid-base imbalance. The patients can have metabolic acidosis, high anion gap alone, or metabolic acidosis, high anion gap with a non-anion gap in the same patient, and which you find contradictory, but it does happen, metabolic acidosis with metabolic alkalosis in the same patient. And the only way to know that is by calculating delta gap. Do you follow me? In today's class, or the next, because we have 2 weeks for that, we're also going to learn that not only the patients can have respiratory acidosis, but is this respiratory acidosis acute or chronic? Patients can have respiratory alkalosis, but is this respiratory alkalosis acute or chronic? Do I have to treat fast, or can I take my time? Okay? Good. So, first of all, there's many techniques how to interpret an ABG, okay? You can choose your own. I can give you some tips, all right? For example, if we start with a pH of 7.29 and a CO2 of 37, okay? Bicarbonate is 19 and the base excess is -8, okay? You have, again, remember that the first number is pH, the second number is CO2, then bicarbonate, and then the base excess, okay? And the PO2 is there in the middle, but we're not talking about PO2 yet, all right? So, you have 2 ways of start your interpretation. First of all, you can say, remember that for those that don't remember, the normal pH is 735 to 745, PCO2 is 35 to 45, bicarbonate is 22 to 26, and the base excess is -+2, okay? So if we start here, you say that 729 is what? Decreased, and is, let's put acidosis, okay? But if you do the arrow technique, it's going down, right? It's lower than 735, so it's going down, okay? Now, the second number that you will gather for the arrow technique is the CO2, not the bicarb, okay? So you compare the pH with the PCO2, okay? Let's do the PCO2. 35 to 45 is normal. Okay, it's normal, but let me show you something else. In every single mathematical equation, there is a medium, right? Medium number and mode, right? That's research, right? Medium and mode. So all the numbers have a medium, right? And you need to know the medium of the numbers. For the pH, the medium number is 7.4. For CO2 is 40, for bicarb is 24. You need to memorize those numbers because you need them for the calculation, okay? So, if I put the arrow like this as normal, but if I now take my medium number as the range, how is 37 compared to 40? It's going down, right? Yes or no? Yes. Even though it's normal, because let me go back a little bit and tell you that you can have a normal ABG and that patient can have underlying acid-base imbalance. Okay? So don't trust the normal ABG and say this patient is perfect. Okay? So if you see now, having 40 as the median number, this 37 is moving to the acid side, even though it's normal. Are you following me? Mm-hmm. Good. So if I take into account the arrows, if they go in the same direction, it's metabolic. If they go in opposite direction, sorry, I see respiratory. Okay? So that is one way, taking the pH and your PCO2 and draw arrows. Are they going in the same direction? Metabolic. They're going in the opposite direction, respiratory. Or, as many do it, this is acid, this is normal part compared to the medium going to the acid side, yes or no? Mm-hmm. And metabolic, acid, why? I'm sorry, alkaline side, sorry.
19? So
It's acid, yeah, but this is alkaline. Why? Because remember, CO2 is the value of acidity. The lower the number, the more alkaline. The higher the number, the more acid, right? So, since it's going lower than 40, it's moving to the alkaline side. And metabolic, bicarbonate is 22 to 26, medium 24, and I have 19. So lower than 22 is acid. So the other way to say is you already plug your acid-base imbalances and you say, what matches my pH? What matches my pH is bicarbonate, right? So therefore, since bicarbonate is the metabolic component coming from the kidneys and many electrolytes, right, buffers, I have a metabolic acidosis. Do you understand? So you can take the arrows, you can label the components, and you can decide, but you have to be in agreement with the first primary acid-base imbalance. So far, so good? Okay. So, if you know now that I have a metabolic acidosis, you look at the other component to see if you have a compensatory buffering system. You remember that if you have a metabolic disorder, who compensates is the lung, right? And that is a fast buffering system. It acts in minutes and hours. Compared to the kidney, if you have a respiratory primary condition, the kidney takes days and months to occur. So when you receive a patient with a respiratory primary condition and you see that the bicarbonate is already compensating, it's already elevated, that for a fact is a chronic condition, okay? So again, knowing that I have here metabolic acidosis since my pH is matching my bicarbonate, I need to look at the opposite value. And the opposite value is the CO2. Is the CO2 moving to the opposite direction of acidity? Yes, it's going to the alkaline. So I do have a compensatory metabolic acidosis, but it's not full compensating because the pH is not going back to normal. Do you understand?
Are you still call it compensated?
It's still compensated, but it's partial. Okay? Now let me give you a normal ABG so you can see that the patient has an underlying condition. Okay?
Wait, hold on. It's partially compensated because there
The pH is not going back to
the
normal.
pH is not normally right, but there is.
It's trying to compensate because the PCO2 is moving to the alkaline side. Okay? Do you understand? Okay. So, if I know now that this patient has a metabolic acidosis before I give you the normal ABG, what will be the next step? The next step, and I did all the steps there for you, as soon as you recognize, listen to me, as soon as you recognize that this patient has metabolic acidosis, because this only applies for metabolic acidosis, you will calculate the anion gas. Because remember, an ion gap only is calculated when you have a patient with metabolic acidosis for the only reason to know if it's high or normal, to know the etiology of the patient. Do you understand?
You need to that if it's metabolic.
Correct, correct. If you receive an ABG with a respiratory condition, you do not have to calculate the anion gap. If you have a metabolic alkalosis, you do not have to calculate the anion gap. The anion gap is only calculated for metabolic acidosis. To know if you have a high anion gap or a normal anion gap, to know the etiology. So far so good? So, but for that, unfortunately, you need to know sodium. So you need to have your BMP, right? You need to know your sodium. You need to know your potassium. If you would like to include your potassium in your calculation, you need to know your chloride, and you need to know your CO2. Please have in mind that the CO2 in the anion gap calculation is not the CO2 in the ABG. It's the CO2 in the BMP. Now, many times, if we don't have that, and we only have the ABG, because you know that the CO2 in the BMP is the value of alkalinicity, is the value of bicarbonate. Don't be confused. The CO2 in the BMP, this is the BMP, sodium, right? Potassium, chloride, CO2, BUN, creatinine, and glucose. This CO2 is not the CO2 of the ABG. This CO2 is the value of alkalinicity. It's the value of bicarbonate. So sometimes if I don't have my CMP yet, and backwards apply, if you don't have your ABG yet, you can determine based on the CO2 if the patient has metabolic acidosis or alkalosis. This value should correspond minus plus to the value of the ABG. In other words, what's my bicarbonate level in the ABG? 19, right? So this value here, I'm expecting it to be 19, 17, 21. It has to be in that range. Otherwise, it's an error.
The ABG's lifesaver, the CO2 that they give, is it this one or does that matter? It's this one, right? When they do their lifesaver time?
Okay? So far, so good? Okay, so let's create numbers. Again, I have a lot of examples in the PowerPoint, but let's create numbers. Okay? So, first of all, you have to memorize the formula for anion gap, which, if you do not include the potassium, which I never do, is sodium minus chloride plus CO2. As you can see, if you do not use the potassium, your normal anion gap is 16. But because everything has the medium and it's from 10 to 16, the medium number which you need to also memorize for anion gap is 12. Do you understand so far?
Or is it CO2 or bicarbonate?
What?
So you're writing there CO2, but CO2.
Oh, I'm sorry, yeah, bicarbonate. I said bicarbonate, but I'm still over there. So, if you have an anion gap greater than 16, not using potassium, you have a high anion gap metabolic acidosis. Do you understand? The other formula is, if you like to include the potassium, which why? Sodium minus chloride, say plus potassium, minus chloride plus CO2. I keep saying CO2 is bicarbonate. Because it's a representation of the CO2 in the BMP. Okay? That's when I tell you that you can get this bicarbonate. If you don't have an ABG, you get it from there. If you do not have the BMP, because sometimes, I don't know if you have seen in the laboratory that the BMP is not complete, and you have some values, you have the sodium, you have this, but you have the yesterday's value, you're not gonna use yesterday's value, you're gonna use today's value, and today's value is the CO2 hasn't been reported, okay? So, because that CO2 is the representation of bicarbonate, you can come to the ABG and get the bicarbonate in the ABG, because again, it has to be the same number minus plus 2.
Why you don't include the potassium in the formula?
You don't have, you can't.
You really don't have to. Remember, the potassium goes freely in and out of the cell whenever it wants to. So it's not a reliable formula. The most reliable formula is when you exclude the potassium. But if you would like to include the potassium, you get the sodium plus potassium minus chloride plus bicarbonate. Okay?
There is a difference. It's a big difference between 16 and 20 without including the potassium. No?
No, it has to be exactly the same. Listen, let me show you. For example, imagine that I have here 135 minus 119 plus, let's put 19, okay? So first you have to do, which you should know, addition and then subtraction, okay? So 119 plus 19,
138.
138, well, in this case, it got actually higher. It couldn't be negative. Let's put 109 here. 109, okay? So, 128. So you will do 135 minus 128, 7. So you get 7 here, okay? So 7, is that higher than 16? No. So you have a normal anion gap metabolic acidosis. And the only thing that this is telling you is that I don't have, for example, diabetes ketoacidosis. What I have is a GI problem. Most of the time, fistulas, diarrhea, NG tubes, colostomy, GI problems is what gives you non-anion gap metabolic acidosis. Okay, the majority.
When you said 10 to 16, the normal, that's the normal range, so if I have a 10, it will be normal?
Even if you have 2, it's normal anion gap. Because the only thing that you're trying to know right now, if it's high or not.
So if it's at 16 will be that mark?
Yes.
Higher than 16?
Higher than 16 is high anion gap. Less than 16, let's put it that way, normal. Okay? Now let's include the potassium. I have my 135 plus, let's imagine that is, I don't know, 2.3, 2.8, okay? Or let's put it normal, 4. 4 minus 109 plus 19. So we know here that this is 128, right? So 135 plus 4 is 139. So I have here now 139 minus 128, which is 9. No, it's actually 11. So again, does it change the result?
No.
11 is less than 20, and it still have a normal anion gap metabolic. So either if you include or not include the potassium, the result has to be the same. And that result is a normal anion gap metabolic acidosis. Do you understand? Now, what is this valuable? If I have, for example, salicylate toxicity on a patient, that's not going to change your approach to the patient. You're still going to alkalinize the urine, right? You still might give sodium bicarbonate because it's a treatment for salicylate toxicity. But prognosis-wise, you know that since the patient is only having a normal anion gap metabolic acidosis, this patient, for example, might be only 24 hours in the ICU and then transfer, compare if my result is a high iron metabolic acidosis until you don't correct that high gap in the formula. If your patient continues to have day by day a result greater than 16, you have to keep that patient in the ICU. Have you heard in patients admitted in the ICU diabetes ketoacidosis that one of the questions says, have you closed the gap? That closing the gap means that have you done the calculation again day by day, and now the patient is less than 16. If the patient remains higher than 16, you can't move the patient out of the ICU because the prognosis is poor. The mortality is high. Do you understand? Okay? So not only the etiology that you will find out, but in addition to that, where do I admit my patient? What kind of follow-up, transfers, consultations? What kind of prognosis does my patient have? Is my patient getting better or worse? Okay? So if you don't like math, this is getting complicated.
So where does the, in the iron gap, the middle number that you said 12 comes in? Sorry? In the iron gap, where you put the mean, was 12?
You're thinking too fast.
Where do we go that everyone?
This is gonna make sense when we start doing cases, okay? So don't panic. Sorry, lock me out.
Share
I think my method is the best. It's easiest method.